Here's the solution to problem number 16 from section 8.2. The question is pretty straightforward to find the limit of the sequence, but it does ask a question about monotone and bounded that has caused some questions to come up. So let me just say what those would be in this case. So the function here is 3n cubed over n cubed plus 1. This is a good example of a function that we could analyze using calculus tools. We could change all of the n's to x's. And again, the idea is that the sequence is only hitting the hitting dots, where the n's going in have to be whole numbers. And this function that I'm writing down with x's allow x to be anything. But that was like a bread and butter calculus problem. So we could ask about the limit as this goes to infinity. I mean, as x goes to infinity, we could ask about horizontal asymptotes of this graph. We could ask to show that this is always increasing or always decreasing. And so all those questions are questions that we already have in our calculus toolbox, and the answers to those questions will be the same answer for these sequences, as long as this has a limit. As we saw in class, if this doesn't have a limit, if this is bouncing around and doing something weird, then we have no idea what's going on this. But if this has the property of convergence, then this will inherit that. To see that graphically, let me just show you some pictures. And I want to make sure you realize that, especially for sequences, we have lots of tools available here. We can see that it kind of makes sense that that's true. If that were 3n cubed over n cubed, that would be exactly 3. But we've kind of moved the denominator up a little bit, which means this fraction is always slightly less than 3. If we want to do a more careful analysis, we can use our formal tools that we talked about in section 4.7 to work out what this limit is. We could use either L'Hopital's rule, or we could use our algebra tricks. The algebra trick here, just to remind you, would be to identify the highest growth term, which in this case is x cubed. There are x cubed in the problem, and that's the biggest growth term that I see. That's supposed to be quotes. That's pretty bad. So x cubed is the highest growth term. So I can multiply top and bottom by 1 over that. And as long as I'm multiplying top and bottom by exactly the same thing, I'm not changing the value of the fraction, so I can't be changing the value of the limit. In the numerator, if I multiply through, in the numerator I'll just have 3, and the denominator I'll have 1 plus 1 over x cubed. And so what we normally do now that we just have little fractions that are simple, I can look at each one. That one goes to 0. That's the only place where there are any x's, and so this limit goes to 3 over 1 plus 0, which is 3. So the picture that you see here on the left, this picture, I just drew that in Excel. So I put in pairs, I put in 1 comma, I put in a column that says 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I put in as the second coordinate the values of the sequence, and I just went and said make a chart with dots. So if you ask, this is a scatter plot in Excel. So if you Google how to make a scatter plot in Excel, then you can figure out how to make this kind of picture. The picture is very valuable here because we can see the sort of the lowest and highest dots that will ever be achieved. So the lowest dot is at 1.5. So we could say this sequence always gives us values above 1.5, so that's a lower bound on the sequence. The upper bound of the sequence seems to be 3. It seems like we're getting close to 3, but never quite reaching 3. If we go back, and our graph does bear that out, keep in mind this is the graph of the function with x's in it, because it includes all the points. You can put in x equals a half, or x equals a third, or x equals 2 and 2.75, or whatever. You can put any x in and get a y coordinate, whereas this picture is the picture of the sequence, where we are only putting in n equals 1, n equals 2, n equals 3, n equals 4. But, of course, let me just get rid of this one. I have, well, maybe. If you have the facility to do it, well, I'm having a little trouble. Let's see. Okay, I think I got it. Here's a picture with both things on it. So the curve is f of x equals 3x cubed over x cubed plus 1, and the dots are the sequence a sub n equals 3n cubed over n cubed plus 1. So this shows both things. So the dots are the sequence, the curve is the function, the f of x function, and we can see that since the limit of this function, using our tricks from section 4.7, we know this limit is 3, and so therefore this limit has to be 3. But more to the point of the question that was asked, this curve does not get above 3 ever, and so these dots can't get above 3 ever. So the upper bound for this curve is 3, and it is monotone increasing. So monotone just means it doesn't change direction, but the dots are always going up, albeit very slowly eventually, but they're never coming down again. So they're always going up, so it's monotone, and they're never getting above 3. So that is the upper bound. So that question is not a hard question. If you look at a graph, it can be a very challenging question if you don't have a graph available to look at. So I'd encourage you to figure out a way to draw the pictures, and like I said in class, if you have a device you want to use, a calculator, a computer, anything, if you stop by my office, I can show you how to generate the pictures that you need to look at to do the homework problems. There are lots of tools available, and so it's just a matter of learning how to use the one that you have most easily available to you while you're working on the homework.